By many accounts, the planet Earth first coalesced into solid mass about 4.5 billion years ago, when the surface of primitive Earth cooled below the boiling point of water about 3.8 billion years ago. The atmosphere consisted primarily of gases, including high concentrations of carbon dioxide, carbon monoxide, water vapor, dinitrogen gas, and hydrogen chloride, and small amounts of methane. Within a relatively short time, perhaps as early as 3.6 billion years ago, photosynthetic bacteria appeared. Photosynthesis then, as it does today, released oxygen gas from the combining of carbon dioxide and water. Carbon dioxide plus water plus light produces carbohydrates plus oxygen. The bacteria released enough oxygen to rust iron near the Earth's surface and produce layers of rock called banded iron formations. These rocks contain thin layers of iron oxides alternating with iron porous shale and chert. The iron oxides are red, the chert is black. As photosynthetic bacteria proliferated during the next billion years, their photosynthesis depleted carbon dioxide in the atmosphere to below 10% and released enough oxygen to exhaust most of the methane in the atmosphere. Methane plus oxygen produces carbon dioxide plus water plus chemical energy. Methane is about 23 times more effective than carbon dioxide as a greenhouse gas. A greenhouse gas is one that absorbs a significant amount of electromagnetic energy emitted by the Earth and warms the planet. The net loss of two greenhouse gases, carbon dioxide and methane, sent global temperatures plummeting about 2.4 billion years ago. As its ice mass grew, Earth reflected more solar energy and became colder still until perhaps the entire planet froze. An episode known as Snowball Earth. Recovery from this frozen state was slow. Volcanoes continued to release carbon dioxide at a steady rate, but photosynthesis and weathering of silicate rock, processes that deplete atmospheric carbon dioxide, virtually stopped at the low temperatures, and thus carbon dioxide gradually accumulated in the atmosphere. After about 30 million years, atmospheric carbon dioxide reached a level at which Earth retained sufficient solar energy to thaw ice at the equators. Once sunlight struck open water and bare ground instead of ice, Earth absorbed more solar energy. Additional water vapor, another greenhouse gas, entered the atmosphere and further accelerated warming. Snowball Earth melted. Indeed, with this melting, Earth's energy balance shifted and a heat wave persisted from 2.4 to 2 billion years ago. High temperatures plus high carbon dioxide levels stimulated a photosynthetic bacterial bloom that released massive amounts of oxygen. Atmospheric oxygen concentrations jumped from less than 0.02% to about 3% in what has been entitled the Great Oxidation Event. This had major biological repercussions. Many simple life forms, which had theretofore dominated Earth, could not tolerate exposure to high oxygen concentrations. Today, descendants of such organisms are limited to a few remaining low oxygen environments on Earth, such as bogs and hot springs. Organisms comprised of cells that have many internal compartments, the so-called eukaryotes, appeared after the height of the Great Oxidation Event. This was no coincidence. Internal compartments such as mitochondria isolate the dangerous oxygen reactions of aerobic respiration that generate about 5 times more energy than anaerobic respiration. The energy bonanza of aerobic respiration fostered the development of more complex organisms. Additionally, higher oxygen levels gave rise to an ozone layer in the atmosphere that screened out ultraviolet radiation harmful to life. Eukaryotes could complete relatively long life cycles without extensive UV damage.